those of you who do not follow this field, so Barry is known in the community of quantum optics, in people that are interested in things like both the fundamental and applied aspects of it. So he worked on the notions of quantum measurement, on the notion of various properties of light, quantized light, and various aspects of secure communication. And more recently, his interest goes into optical implementations of quantum information processing and also quantum algorithms. From 2017, Barry is also a fellow of the Royal Society of Canada. But you know, titles aside, Barry is a fantastic researcher and a good friend, and it's such a great pleasure to have him today for our colloquium. It is, I understand, 9 p.m. so on Barry's side, and it's 11 a.m. here in Singapore. We hope not to tire you too much with questions and so on, but nonetheless, you know, we are very interested in your thoughts about this parity time symmetry as a time-dependent inner product in Hilbert-space. So, Barry, I should say the floor or the screen is yours.
Okay, first I want to say, really, it's a great pleasure to be able to give this colloquium, and I'm great. Arthur is one of the busiest guys I ever know, and I'm really grateful that he's taken the time to introduce me and join this colloquium, because I don't know how many things he has on the plate, but I know the lower bound on the number of things that keep him busy, and I'm sure the actual number exceeds that. So it's great, and it's great to see Arthur again. As Arthur said, it would have been nice to come out to Singapore. I was supposed to come in May, and this pandemic hit, so we're all staying home. I'm hoping that I can convey with you with the same degree of excitement online as I would have if I were in the room moving around and raising my voice and so on. Okay, so it's great to be able to give this talk. Now I need to be very clear. I'm going to talk about PT symmetry, which is a hot topic now. The direction that I've been going, working closely with my student, Shalini Karvade, and my postdoc, Abhijit Alais, is to kind of sort through it's a burgeoning field, but there's still a lot of unclear points to what PT symmetry is about and what it shows. And so some of this presentation is necessarily mathematical, but the message that I have to give is relevant. Not just, it's relevant in mathematical physics, it's relevant in theoretical physics, and it's relevant in experimental physics. And in experimental physics, there are many papers a year in many, even the topmost journals on this particular topic. And so I believe that even though our focus is a mathematical physics focus, and I'll just kind of give an overview of it, the idea is to convey the concepts and to sort out where PT symmetry fits into quantum mechanics. And the title kind of gives away the message that PT symmetry is about inner product. Now, this has been known for 17 years. Mostafazadeh in Turkey made clear that PT symmetry was her mission by adjusting the inner product. What Shalini, Abhijit, and I have been much more interested in lately is not the idea of PT symmetry, but the idea of changing PT symmetry. So you can imagine that, you know, if we live in our universe is quantum mechanical, what if tomorrow the inner product on Hilbert-space changed? Or what if the inner product on Hilbert-space were different in Singapore than in Calgary? How would that affect things? So this is the issue that we're addressing, is how to think about PT symmetry in some space-time varying way. Now, the concepts can get deep in that respect. We're keeping it down to what I think of as a two-agent protocol. So we're just going to consider two agents. They can be separated in space, separated in time, and how the inner product affects it. And in order to do that, we need to go back to our concepts of quantum mechanics. And so in quantum mechanics, we are taught that, so in orthodox quantum mechanics, the Copenhagen interpretation, we're taught that every state is a ray in Hilbert-space, and then we kind of loosely gloss over what Hilbert-space is. But Hilbert-space is a complete inner product space, and And the idea of the inner product might not be unique. So we say that every state is a ray in Hilbert-space. Which inner product do we pick on Hilbert-space? And this is something we tend to ignore. And it turns out that one inner product is as good as the other. But what if the inner product were to vary over space or over time? So that's kind of the concept beneath it. And the many experiments that go on, we think about as being related to studying the inner product. It's not the way it's discussed in the literature, but we think that we've got a framework where this is the way to think about it. So that's the idea. Now, after all that, I'm ready for the first slide. So here's the first slide. You can see in the upper right a nice picture of Calgary. That's downtown Calgary, the river flowing through it, the mountains in the background. Calgary is a nice place to be. It's often rated the cleanest city in the world. The water in the river, you can actually drink out of it. So if we ever get over this pandemic, you're welcome to visit, and it's a nice place to be. On the left, you can see the breakdown of how this presentation is going to go. I'll take some time to introduce, and then we'll cover background. Now, even though the Colloquium has me in it, normally with colloquia, you know, I would fly somewhere and give a colloquium. Nowadays, there's an opportunity to feature the people who did the real work. So I'm here giving the colloquium, but the real work was done by my student Shalini and my postdoc Abhijit. And so I want to recognize what they do. They're both excellent communicators. So at 2 slides in the background, one of them will present one slide, one of them will present the other. I think it's good that you actually, all of you, get a chance to see and hear the people who really did the work behind it and hear their presentation. So I will do almost all the slides, but they'll do a couple. After the background, in one slide, I'll explain to you the approach that we're using to solve these problems, and then I'll give you the results. Now, everything is hot off the press. We're still getting results today. So it's kind of a risky colloquium to give because I promised to give it, and the promise is then concomitant with the need to do so. So the pressure of delivering this colloquium today means that we've been working many hours over the last few days getting everything ready. So when I get to the last few slides, you'll see things are, the last couple of slides are a little bit thrown together, and that's proof that it's hot off the press. That's the idea. But I think the message will be clear, and then I'll conclude, and you can see that I like social media, so you can't miss me. There's various ways to reach me. Okay, let me go down to the next slide. Whoops. Okay, so I like to make clear at the outset what the point is. And you'll see on this slide some mathematical expressions. So there's mathematical physics involved. I know that could be scary sometimes. It's not essential, but I want to make clear that some of the stuff we're doing involves innovation in mathematical physics. So I'm going to say what it is, but if you're not so inclined, you don't need to focus too much on what's said, but it is an important message. Okay, so our aim here is to operationalize PT symmetry that incorporate agents with different PT symmetries. So as I said earlier, it's kind of like saying, what if the universe had an inner product that varied with space and time? What would that do? But the way that the field works is people care about PT symmetry. So the aim here is to operationalize PT symmetry. Operationalizing it makes it equivalent. What do I mean by operationalize? Well, so operationalism was introduced by Bridgman about 80 or 90 years ago. And Bridgman was addressing the question about why Einstein was so great and all the other physicists were kind of left in the dust. And so Bridgman came to the conclusion that operationalism, which is founded in logical positivism, was important. And Einstein's thinking about things like the speed of light, he's imagining being on a train that accelerates the speed of light. In a sense, he was operationalizing. And what that means is that in the way Einstein did, he had a clear idea of how to prepare and how to measure. The geometrodynamic clock, how you measure the passage of time in general relativity, Einstein imagined an ideal clock. And so operationalism emerged out of that kind of thinking. Mathematically, it came into C-star algebra. So quantum mechanics presented a lot of puzzles. And then in the 1940s and 1950s, operationalism led to the C-star algebra framework. So when I want to operationalize something on the physics level, I always want to be careful to explain in a plain description what's prepared, and in a plain description what's measured, and in a plain description how it's interpreted. And then mathematically, I need to use a C-star algebra to describe it. C-star algebra is not part of the usual quantum physics training. So I realize a lot of us quantum physicists can get by without it, but often we need it. And things like you might know about Stein-spring dilation, Krauss operator representation, and a lot of proofs to do with quantum computing actually are founded in C-star algebra. So it's there. Sometimes for some problems you really need to, it's the best way to handle it. And it turns out here. Okay, so we're operationalizing. We're saying PT symmetry needs to be considered in the sense of preparation and measurement. And when I say incorporating agents, the literature tells us the hints that we need to know for a single agent. So if the inner product is the same across the universe, or PT symmetry doesn't change, then dating back to Mostafazade's work, we know that it's all standard quantum mechanics. But if it varies, then it's not well posed, and that's the purpose of what we're building here. Okay, the claims that I'm now listing. So I got 5 claims to make in what we've done. And these claims are things that emerge out of this work that we're proud of. So this claim block is really just telling you what we think we did that's significant. And the first 2 are mathematical and the other 3 are procedural. Okay, so the first one is, now I'm going to explain this one carefully and it will become clear later. But the first claim considers the star operation. And so the star operation, when we say things like take the adjoint, and usually in quantum mechanics, we even have a license to mix things up at times. We'll talk about the adjoint of an operator, or we'll talk about the Hermitian conjugate. We might say an operator is self-adjoint, or we might say that an operator is Hermitian. But really what happens is if we talk about Hermitian, we're talking about the representation of the operator on a Banach space of operators, and those are the operators on Hilbert-space. But if we talk about adjoints, we're talking on the algebra level. And this is important to distinguish the two. Things like that not every operator has a conjugate, there's problems in infinite dimension, there's all kinds of things that come up where you have to be careful between the algebra and how it's written. The way to think about it is if I write an operator, like a position operator, angular momentum operator, number operator, and then I write its matrix representation, or I say that momentum is like the derivative of position, these are then representations of the operator. And so what we've done here, what we're doing is the star operation on the algebra is like the adjoint, the Hermitian conjugate, if you like, it's like that. And so we're saying that we're considering how to do the star operation and change what the star is. So I've got an asterisk, I'm going to call that the 6-pointed star, and then there's a 5-pointed star. So if we change the star operation, we're changing the adjoint. But what does it mean to change the adjoint? When you take an operator and you consider the adjoint of the operator, like the transpose of the conjugate, what's happened is you're just considering by the inner product how to move the operator from the right side of the inner product to the left. That's what goes on. And so when we're changing it, the idea of changing the way that we take an adjoint is about changing the inner product. And the reason this is important to us is we're taking the concept of the changing inner product. So I'm telling you that PT symmetry is like a changing inner product, and then we're lifting it, and you'll see the word lift is technical, and we lift it up to the point where we're able then to talk about what's going on with the operators themselves, regardless of the representation. And so one point we make is that the change of a star operation, how we take an adjoint, is equivalent to changing the inner product. And the inner product, you can see parentheses with 2 bullets representing arbitrary representations of operators. And then we just plug in an eta, and it says that eta lives in, now the calligraphic A is the C-star algebra, I'll explain it. And then the eta is a member of the positive definite element. So as long as eta is a positive definite operator, then we're able to connect the change of the inner product to the star operation in a C-star algebra. And I'll explain it more. Okay, the second claim we have is that for every star operation, for every map, changing of the star operation, such that the star operations described by some eta, this is known as the relative metric in the literature, that as long as it's a positive definite operator and it's less than or equal to the identity operator, then there always exists a channel that has the following properties. It maps pure states into pure states, and I want to be careful. Normally a pure state is a state that squares to itself. Rho squared equals rho is how we normally write it. We're relaxing the definition. We're saying as long as rho squared is equal to some real number times rho, we're calling that pure, because we're allowing, if the inner product changes, the norm changes. And so E is it preserves pure states in that sense, and it's a completely positive trace non-increasing map, which I'm going to call the noiseless lossy quantum channel. Then we prove that every change of the star operation, how we make an adjoint, is equivalent to constructing a noiseless lossy quantum channel. This is part and parcel of experiments, but at the moment, things are a little bit ad hoc in how it's done. This is important for our agenda of considering how the inner product changes over space-time. And so this mapping, the changing of the star operation, can always be represented by a noiseless lossy quantum channel. And that connects with the experiment. So we're now able to tie how experiments work to that. Furthermore, we're going to be able to devise new ways of dealing with the changing inner product. Those are the two mathematical results. Then the third one is really a procedural one. It says that we can take the concept of PT symmetry and the one agent case, we operationalize it. So as I said before, prepare and measure. But we're now able to do multiple agents. So instead of me talking about how it changes in space-time, as I said before, we can consider an agent at one point in space, another agent, another point in space, or same point in space, different point in time. And then we can discuss PT symmetry in terms of the two agents. And we're working our way towards an uncountable number of agents to fit with space-time. Okay, so we've operationalized that. That's a new result. The fourth claim that we're making is that that channel can be devised given either the Hamiltonian that is PT symmetric, and I'll explain PT soon, or we can have the inner product change. So if you tell me the Hamiltonian and you promise me that Hamiltonian is PT symmetric, we can apply our algorithm to construct the channel, or you can tell me the relative metric eta. Both arise. So PT symmetry was first put forward by Carl Bender. So Carl Bender's first paper we'll mention came out in 1998. It created a lot of activity in the field, and Carl Bender would write down crazy non-Hermitian Hamiltonians and get physics out of it. So if Carl Bender tells us a PT symmetric Hamiltonian, we can construct the channel. On the other hand, more recently, there are tasks. Cloning. So the idea, the questions come up. Can something be cloned violating the no cloning principle? Is superluminality possible? And so these tasks can then be identified with the changing inner product. And if you tell me, you say, here's the task, we identify the change of inner product represented by eta, then we can devise a channel that goes with it. And by devising the channel, we're able then to map it into the experimental world. And the final claim we have is that we have devised a qutrit simulation of unitary dynamics in one system. So basically, we can consider two agents, establish the change of inner product or the PT symmetry transformation between two agents, say Alice and Bob. Then we're able to dilate it into a unitary dynamics and a qutrit. The fact that we can make it unitary is not entirely surprising, but the standard procedure is Stein-Spring dilation, which would take 1 qubit to 3 qubits. The fact that we can do this with only 1 extra Hilbert-space dimension instead of 4 extra makes it highly efficient. So we can show that the qutrit simulate, that a unitary qutrit dynamics will simulate the qubit case and show some interesting results. Okay, now that my talk's half over, now we'll go to slide 3. I promise not to run over. Here, the novelty and the importance. So I want to just get across what's new. After this slide, we get into technicalities. So what is new about what we're doing compared to what the rest of the universe that we know does is, number one, we're employing the C-star algebra approach for operationalizing PT symmetry. It's the newness, we're being very explicit about it, but you can see in work, for example, by Brody, the thinking is there. So it's new, it's not a revolution, but we are being very careful to formalize everything in C-star algebra. The second part, and this I think is a really interesting feature of what's coming out. So in structural mathematics, also known as category theory, there are ways to prove relations that make use of diagrammatic techniques. And so we're able to prove things here by using the diagrammatic methods that are common in category theory. We could do them in other ways, but the diagrammatic techniques have made the proofs that we have to have much simpler. And we'll show you examples of that so you can appreciate why that's a good technique here. And then finally, the idea that we can dilate the qubit to qutrit was not a priori obvious. And so the fact that we only need one extra dimension to simulate PT symmetric transformations was a surprise to us. And why is it important? Well, first of all, Mostafazade's proof that the changing PT symmetry in the universe is not observable was very important. So PT symmetry was considered to be an observable effect. And back in 2003, Mostafazade showed it's not, that it's equivalent. But nobody touched the point of whether the inner product could be variable and maintain quantum mechanics to be the same. Now, I wish I could tell you that we did this and discovered quantum mechanics is different, but we're able to fit everything into quantum mechanics. So by being careful with how we formulate quantum mechanics, we show that everything is compatible. So that should help you sleep at night because quantum mechanics didn't change, but it's important to know that. And by doing this, we've also set the stage for a number of theoretical and experimental investigations because we're opening the door to being able to study how this inner product variation would work. So our way of mapping, taking these star transformations to inner products, but connecting that with channels allows us to bring the physics into it. Okay, now, so that kind of leads into how we motivate it. So first of all, the motivation came out of questions that pre-exist what I'm telling you today. One is the idea, is it compatible? I already told you the answer to the question, but there have been papers that have come out that have said that PT symmetry could lead to superluminality. It could lead to violation of the no cloning principle. So it kind of reminds me of the old days when Wouters and Zurek even did the no cloning proof. There was a question about superluminality. So by proving the compatibility, we're definitely putting to rest the idea that changing the PT symmetry could lead to some really strange things. That won't happen, but that's part of our motivation. Another one is even if quantum mechanics works, could that change the complexity classes in quantum computing? So I'll say the inner product, if the inner product varies between 2 points of the universe, could you build two quantum computers at different points? Quantum mechanics is still respected, but could you run part of your quantum computation in one place, send it to another place to have more computation done and have it sent back? Would that change the complexity class? And so I'm not going to answer that tonight. That's the one that will keep you awake. So the third point is what's observable. So as Mostafazade pointed out, PT symmetry, changing the PT symmetry is not an observable effect, but a relative PT symmetry is observable, and that's what we make clear. So if 2 points of the universe have different PT symmetries, it is observable to see that change. And that leads to the experimental PT symmetry. And so we're saying not only that it would lead to an observable effect, but that every PT symmetry can be represented by a noiseless lossy channel. In experiments, what typically happens, so I've been co-author of some beautiful experimental papers. I say they're beautiful, I'm a theorist, so I didn't do the experiment. So when I say my papers are beautiful, the beautiful part is the experimental parts I didn't do. And in those experiments, we need noiseless lossy channels. And so one of the tricks that we can do is we'll make losses, which can be effectively noiseless. But then if we change the norm more than some of the loss, we can say that a weak loss is a gain. It's a mathematical trick to do it. So we're able to play this loss gain trade-off and say that we're simulating this PT symmetry. And so we can now take that notion higher and be able to devise it. And if any experimentalists are worried you don't know how to make a noiseless lossy channel, the noiseless part can be, there are mathematical ways to justify them. Okay, now if you don't mind, I want, Shalini is going to present this slide. Abhijit will present the next one. And then you'll be disappointed to learn that my much more casual ad hoc way of talking will return. So the two professionals are going to present 2 slides. So Shalini, take over for this slide.
Thank you, Barry. I will now talk about, I'll give a brief overview of the field of PT symmetry, especially focusing on how the field evolved over time. As Barry already mentioned, PT symmetry quantum theory was introduced in 1998 by Bender and Boyker. The theory was originally introduced as an extension to standard quantum mechanics. So the idea behind introducing PT symmetry quantum mechanics was that the condition of hermiticity on the system Hamiltonians was relaxed, and it was further replaced with 2 different constraints. The first one is that about the Hamiltonians possessing real eigenvalues, and the second one is about the Hamiltonian being invariant under the combined action of an antilinear symmetry called the PT symmetry. Later, Ali Mostazadeh showed that a special class of PT symmetric Hamiltonians, we call them the exact PT symmetric Hamiltonians, are in fact Hermitian if one appropriately changes the inner product of the underlying Hilbert space. This is quite interesting, especially considering that the original intention of PT symmetric quantum theory was to get away with the hermiticity condition on the Hamiltonians. So building on this result by Mostazadeh, Brody further showed that a closed quantum system that evolves under a PT symmetric Hamiltonian, that is exactly PT symmetric, is in fact equivalent to a standard quantum mechanical system. Therefore, an exact PT symmetric system does not violate any fundamental information theoretic principles, such as the impossibility of superluminal signaling or deterministic cloning of non-orthogonal quantum states, etc., that Barry discussed in his previous slide. So this essentially rules out the possibility of observing any PT symmetric signals in a closed physical system. However, it does not rule out the possibility that PT symmetry can still be observed in an open quantum system setting, and this in fact is an active area of investigation. There also exist several proposals in the literature that considers leveraging the effect of exact PT symmetry in open quantum setting for quantum information processing tasks such as cloning and state discrimination. So in order to further talk about the mathematics behind PT symmetric quantum theory, I now invite Abhijit. Thank you.
Thanks, Shalini, and thank you everyone for attending today's talk. So as Shalini and Barry already mentioned, the idea behind introducing PT symmetry was to get away with the ad hoc dagger operation, the adjoint operation that we use in standard quantum mechanics. And the brave attempt by Carl Bender was to use PT symmetry that we know from particle physics. So going to the math, generally in the literature, we think of parity as just a linear isometry. Also, you can think of it's the same as a unitary operator. Isometry just means it's a norm preserving transformation. And T, which stands for time reversal, is any antilinear isometry. So an anti-unitary operator on Hilbert-space. And we assume that they have special properties, that they are involutions in the sense that they square to identity and they commute with each other. So P, T commutator is 0. And with this, a PT symmetric Hamiltonian is any Hamiltonian that commutes with the operator PT. So there are 2 points to mention. First one is that a PT symmetric Hamiltonian is not necessarily Hermitian. We generally allow any operator H that is semi-bounded to be a PT symmetric Hamiltonian. And secondly, in the commutator, we have H, PT equal to 0, but PT is a anti-linear operator, not a linear one. So despite H and PT commuting with each other, it is not guaranteed that they have a common eigenbasis. Which brings me to the next point, that we can identify a class of PT symmetric Hamiltonians that are known in the literature as exact PT symmetric Hamiltonians. And these are the ones where H and PT not only commute with each other, but they share an eigenbasis. And it is a simple proof already given in the first paper by Carl Bender that if H and PT share all eigenvectors, then H possesses real eigenspectrum. And a very important consequence of exact PT symmetry, which was shown by Mustafa Zadeh, is that for a finite dimensional diagonalizable Hamiltonian, that is PT symmetry, we can always find a positive definite operator eta, so that the equation on the last line, eta inverse H dagger eta equal to H, is satisfied. Let me point out that the dagger operation here is dagger in the sense of representation, as Barry talked earlier. By this, you can think of it as representing the Hamiltonian as a matrix and taking the Hermitian conjugate of the matrix and lifting it back to the Banach algebra. The second point is that the left-hand side of the equation, eta inverse H dagger eta, can be thought of as an adjoint operation with respect to a different inner product. And part of this will again come back as Barry explains the rest of the work. Thanks.
Mm-hmm. Okay, thank you very much, Shalini and Abhijit, for excellent, clear presentations. And I'm going to try to follow your standard now. So to the rest of the people here, I'm going to make sure I don't stray, and I'm going to stay right on topic. Okay, so these things, I'm just going to mention a few points. The slides somehow I'm hoping will be available. So you don't need to follow every word, but the slides are very well self-contained. I'm just gonna, on this slide, I just wanna make sure we're gonna use the term C-star algebra. I just wanna get across what the notion is. And so the C-star algebra, the first reason that we need it is we talk about operators in quantum mechanics, and operators satisfy an algebra. We can add them, we can multiply them, we can also do adjoints. The star is really telling us how we do adjoints, and the algebra is telling us how we combine operators. And so technically, operators in quantum mechanics are associative unital C-star algebras. Probably all of you who work in quantum are used to these kinds of things. You just might not be used to the language. And so it's a Banach algebra, so that means it has a norm on it. The involutive star operation is what you know. The adjoint of the adjoint is the original operator, and it satisfies certain properties. More importantly, there's a connection between adjoints or stars. So the norm squared of an operator is the norm of the adjoint of the operator times the operator, what we know in quantum mechanics. What's important too with the C-star algebra is we have the algebra abstractly, and then we can map it by a representation to the Banach space. What we're used to is, like, if I talk about Pauli operators, you know, X, Y, Z, and then I map it to 2 by 2 matrices, we often think in quantum, you know, like in quantum information, we think that the Pauli operators are the 2 by 2 matrices, but the Pauli operators have their properties, and the 2 by 2 matrices are a representation, and that's what pi does. So you can think of pi as a way of turning operators into matrices, if you like. And then the Hilbert space just is the space of vectors. So matrices are constructed out of vectors. You multiply a ket times a bra and you get matrix. The kets can be vectors, and the matrices and the bras can be covectors. So that's what's going on in this one. What's important is there's a C-star isomorphism. And the idea, this relates to what I said. If Alice and Bob live in 2 different parts of the universe and they have different inner products, then we think of them as having the same algebra, but a different inner product. The C-star isomorphism is an isomorphism that preserves the star operation and the norm. So we can now think about maps between these algebras. And finally, the idea of the channel. So I mentioned to you that we're showing that this change in the star map is equivalent to setting up that channel. So a lot of, I'm sure in the audience, there are a lot of experts on completely positive maps as channels. I just put down here the definition of lossy. We're calling it noiseless if a pure state maps to a pure state, but rho squared is not rho. Rho squared is just is some positive real number times rho. And if we do that, then that's how we define a channel. So we're defining a channel not as a completely positive trace preserving map, but as a purity preserving, completely positive trace non-increasing map, technically. Okay. Now this is the interesting part that shows our technique. So it's proof by diagram, and this proof by diagram is used in structural mathematics, but it's somewhat rare in our quantum field. We're using what's known as a commutative diagram. And so on the right, there's an example of commutative diagram, and the technique of proof by diagram is known as a diagram chasing, or more technically, a diagrammatic search. This is used in mathematics. So an example is homological algebra where it's used. But essentially what you see on the right, this is the concept of a lift. So suppose in that one, we have a unitary map of operators to operators. But we know that a unitary map can be written as a unitary operation on a ket in Hilbert-space. And if we know how the unitary map operates on the ket, and we know how to star it to get a U dagger, we can build up how the operator transforms by thinking of an operator as a sum of ket bra products. That's what's shown here. So the lift is simply lifting the Hilbert space to the Banach space of representations of operators and mapping them. And then what happens is we're able, by using, this is kind of a trivial use of it that we understand as undergraduates, we don't formalize so much, but that's what we use. But the idea is we can prove properties of matrix representations of operators by knowing how vectors transform. And so we're just generalizing this. And the reason we generalize it is we need to relate the star transformation to the inner product. The inner product is on Hilbert space at the lowest level in our diagrams, and the algebra will be at the highest level. The other background thing I need to mention to you is about the qubit qutrit. And so this, we keep a mostly empty slide because I'm assuming most people in the audience know what a qubit is. Just put it here for a qutrit. So a qubit is a two-dimensional system, and we represent it typically by a wire. So the qubit in the 0 state, the wire moves right in time. H in this case is a Hadamard gate, and it transforms 0. So that's the idea. Qutrits, we just extend the dimension. So in this case, it's just an F gate. An F gate does a Fourier transform. So in this case, 0 is mapped to 0 plus omega 1 plus omega squared 2, where omega is cube root of unity. And so we can just think of qutrits as three-dimensional versions of qubits. Okay, in this one slide, I'm just going to convey to you the approach that we use, and then I'm going to hit the results that we get. So this is a sketch of how we prove everything. So there are 4 techniques that we use in our work. The first is how we change the star operation, right? So that's effectively, that's the algebra version of varying the inner product. And what we do is construct the diagrams, and you'll see them. So we use diagrams, so we're able to lift a proof on changing the inner product to a change on the star operation. So by using diagram chasing, we're able to connect algebraic changes to Hilbert space inner product changes and deal with how operators, and connect it with channels. The second one is operationalizing PT symmetry. I mentioned Bridgman. There's a work by Pekka Lahti, Paul Bush, who unfortunately passed away a few years ago. I forgot the third, but there's a book called Operational Quantum Mechanics, came out in the 1990s, and I love what that message is. So essentially, I like to follow the techniques that they write about in the book on operational quantum mechanics. Here we clearly describe preparation, we describe the process evolution, we describe the measurement, and we do so in the 2-agent protocol. So we make sure that we describe operational PT symmetry in the spirit of Bridgman and in the techniques of Bush, Lahti, etc. Okay, the third point we do is devising a channel. And so in order to, if you tell me, like Carl Bender would have, your HPT, your parity times symmetric Hamiltonian that's not self-adjoint, or you tell me how the inner product needs to change to do a task like cloning, then we construct the channel also by diagram chasing. So we do diagram chasing to connect inner product to star, and we do diagram chasing to devise the channel. And finally, when we embed the qubit and the qutrit far more efficiently than what Steinspring dilation is, essentially what we recognized is that PT symmetric transformations are like can be related to lossy unitary channels. So we realized that we only had to add an extra dimension. So essentially we just write a general qutrit operation, and then we solve standard algebraic relations. I don't mean C-star algebra, but just the algebra that you do in high school. So that's how we do that. So those are the techniques. Now I jump into the results. And so this is just a sketch of how we do it, so you understand what goes on. On the right, this is the diagram chasing we do. And so on the left, some of the terms are already defined and some aren't. But in this case, we're saying that eta is given. So I said, you can give me HPT or give me eta. Eta is the kind, if you told me do superluminality, do cloning, do whatever, if it's possible, we would then construct the eta to do so. So when Shalini presented background, one of them was a paper I co-authored. And in that paper, it was the pseudo-unitary cloning. We did a cloning, non-deterministic cloning. And in that case, it was a matter of finding the eta that would succeed. So in the case where it's task-driven, eta is constructed, and that gives us the top layer. And that maps us from a 6-pointed star to a 5-pointed star. So everything of quantum mechanics is the same, but the way you take the adjoint of an operator changes. But then we go down pi. Pi is the representation. So that takes the operators and effectively writes them as matrices if we restrict to finite dimension. And so the star, the 6-pointed star turns into the ordinary dagger, the 5-pointed star turns into the double dagger. And so at different parts of the universe, there's a different way of taking the adjoints. But those adjoints, we can then take the Hilbert-space change of inner product with the eta term. This is what Mostafazadeh did. And then we apply, it's technically known as a lift, and we lift the Hilbert-space properties to the Banach space, and we're able to connect it. So by lifting the idea of eta that Mostafazadeh introduced, and by representing the algebra that's given by eta and making use of the middle, we're then able to make strong proofs of that that it's only a different, that it's just a change of inner product. And what's important in the bottom layer is that calligraphic I is an identity isomorphism. So the isomorphism converts Hilbert space to Hilbert space of the same dimension, but it also preserves the scalar multiplication of Hilbert space. It preserves the addition, so it's an isomorphism, but it changes the inner product. So an isomorphism between Hilbert spaces allows the inner product to change, but preserves all the other operations. So that's allowed. So then what we've done is connected that with this algebraic change involving eta. Okay, the next result that we get is proving the channel. So I said to you that we show that a PT symmetric transformation, say between space-time points of the universe, can be achieved by a noiseless lossy channel. This is just the sketch of how we do it. So again, you see the same kind of commutative diagram. And here, that A eta is the, that's the algebra under that eta transformation. So we're able to, at the bottom layer, we have two Hilbert spaces. So that's Alice and Bob, Alice at two different parts of the universe. And then on the top layer, this is the algebras that each of them would describe for their local region in the universe. And then what happens at the bottom layer, there's an identity because everything about their Hilbert spaces is isomorphic except the inner product. We lift that up to the gamma on the operators, and the gamma is the adjoint changing operation. And we have E as the channel on the algebra, and then that connects with the gamma. So we're able to prove that every star changing map is equivalent to a noiseless lossy channel. That's the idea. So that's a key result, and that's how we do it. Okay, the next thing is operationalizing exact PT symmetry. So on the left, this is essentially what's in the literature. So what we write on the left is known, and we take a small amount of credit for just writing it in an operational sense. So all we've done there is just done a tiny reinterpretation of what's in the literature, the preparation, the evolution as a closed system, measurement of anything, and then if the measurement data, what it's proved is the measurement data is equivalent to unitary evolution, and the Hamiltonian doesn't have to be self-adjoint. This is all in Brody's paper that Shalini talked about. So the left side is, we're just rewriting the language of Brody's paper, but we're certain that Brody understood and was conveying this, just not exactly the way we are. But we needed to do it because on the right side, we're dealing with the two-agent protocol. So two agents at different parts of the universe. And in this case, we're saying there's a channel. I like to think of it as a wormhole. So there's Alice and Bob at two different parts of the universe. There's some channel like a wormhole that connects the two. And then in our two-agent protocol for PT symmetry, Alice prepares the state. She sends it to Bob. And then in Bob's system, it evolves as a closed system. And one of the ways we've been thinking about it is distributed quantum computing. So one of the examples we like to think about is that Alice and Bob each have a quantum computer. They make this wormhole between them. That's the channel. Alice performs quantum computation, teleports it to Bob. Bob does more computation in his universe. He sends it back. The channel is invertible. He sends it back to Alice. And then they measure. And so what I said I'm not going to talk about today is whether it offers a computational advantage. But we're able to then develop this whole operational protocol about preparation and measurement. And then I told you, so in the left side, the single agent procedure, there's nothing that can be done operationally to detect what your PT symmetry is. So if you want to stay by yourself in your room and do the experiment, you won't find out what PT symmetry applies. It's not a meaningful question. But if Alice and Bob are connected by this wormhole, they can do experiments to infer the relative inner product or the change of inner product or the PT symmetric change. So the right side has a signature experimentally. Okay, this is where you see the hot off the press features. So these next two slides are done 5 minutes before I started. So 5 minutes before the hour. And so these are very brief. Fortunately, we're almost out of time. So this is the way to devise the channel. So I said that Alice and Bob are connected by this wormhole. I should say channel, but wormhole is sexier. So they're connected by the wormhole, but how do they devise it? And so we have a procedure, essentially algorithmic, that says if you specify the PT symmetric Hamiltonian in Bob's part of the universe, or you specify the E that's required to do the task, we then have a procedure to be able to construct it. And that's helpful. People have done it in the past, but it's more ad hoc, and we've developed ways to make it much more algorithmic. And I like algorithmic. If it's ad hoc, you have to be smart to solve the problem. And if it's algorithmic, I can be dumb and be able to know how to do it. So I like things the dumbest way I can. So that's the advantage. The final point that I'm mentioning, and we don't go into details here, is the idea that we're able to do the qutrit simulation. I gave the hint before, we didn't put the details in, but essentially what we do is say, we say that Alice and Bob, Alice is sending Bob the qubit to do his stuff. He sends it back to Alice. Then we say, okay, we believe this is simulatable with unitary qutrit dynamics. We write down the general form. Then we have our qubit PT symmetric transformation. We have our qutrit unitary map. And then we just set some equalities and solve some high school type algebraic expressions. That takes me to the final slide for an on-time finish, I hope. So these are the takeaway messages. So the point is, the first point I want to tell you is that the change of the inner product is equivalent in a C-star algebra to changing the star map. So in order to make things rigorous in quantum mechanics, it's about changing the star operation. For the usual way of learning quantum mechanics, it's what I told you before, that when we're taught that quantum mechanical states are raised in Hilbert-space, the choice of the inner product on Hilbert-space is ambiguous, but once you choose it, that defines unitarity in the rest. We're saying that we're allowed to change it, and on the algebra level, it's changing the star map. On the Hilbert-space level, it's changing the inner product, and we've established some equivalence. And then we say that as long as the representation of changing the star map by a positive definite operator eta that's smaller than identity, we can always it can always be represented by a completely positive trace non-increasing channel. And we have a constructive way of making that channel. That's that wormhole between Alice and Bob. So we know how to build it given eta. We know how to build it given HPT. that once that wormhole is built, the two agents can collaborate to actually ascertain their relative PT symmetry. There's a kind of trick here. If the two agents build it, they already know the answer. But if Charlie comes in and builds the wormhole, then Alice and Bob can work together to find out what it is. And finally, it's experimentally friendly because qutrit experiments are very good nowadays. And so the idea of doing a qutrit realization hasn't been done, and a qutrit realization would be a nice way of planting what we're saying on a firm empirical foundation. Thanks for listening, and thanks for giving me the chance to talk to you.
Well, thank you, Barry. Thank you, Abhijit and Shalini, for your contribution to this talk. Do we have any questions? Let's see, I'm just looking at my chat window, but it seems that there may be questions coming. Don't be shy. Actually, if you have any questions, do type in. Barry, I have to say that, you know, I was a little bit defeated, I have to say, by mathematics in your talk, but I have a few questions. One is a sort of maybe on the interpretation side, and the other one is slightly more technical. So for example, just one of these questions obviously people would be asking is to what extent the phenomenon is something that you can observe, and what kind of conclusions, what kind of modifications you expect. So you were talking about cloning, and so isn't that, clearly you are not questioning here the fact that the operations in quantum theory are linear. It's just you say that you know that the scalar product, the inner product might differ, and so when we prove no cloning theory, there are two ways of doing this. One is using the fact that you want to preserve the inner product, but the other one just simply follows the linearity of quantum theory. So isn't that obvious that cloning will in no way be affected by your consideration?
So yeah, now it's obvious to us it isn't, because once we prove that it has the same foundation as standard quantum mechanics, that's a consequence. But it's an open question, and there is literature where people raised the questions and didn't know how to answer it. So it's not a trivial question, because smart people were befuddled by that. The second thing that's very interesting is once we implement it. So when we implement our procedures, we're led to the probably, you know, so when there's cloning, so there's no cloning theorem, but then there are different ways to clone. So one direction is to clone badly, you know, and then there's an upper bound to how well you can clone non-orthogonal states. And there's a bound. The second one is to clone perfectly, but not deterministically. So a lot of things disappear. In our case, the latter emerges. So the idea that by allowing the inner product to vary or PT symmetry to change leads to the probabilistic perfect cloning protocol was not obvious beforehand, and yet that emerges out of our formalism. Okay, so you say that the perfect cloning remain impossible, but when it comes to optimal cloning, different scenarios, that there will be differences. Yes. No, so there won't be there'll be nothing with cloning that you can't explain with existing knowledge, but the idea that you can explain it all in terms of a changing inner product and get the same probabilistic cloning result, to me, is a surprise. Right, but I guess interpretation might be different. The fidelity, for example, of cloning depends on how you define the inner product, so that will be affected. The second question is perhaps more technical. Before, you know, I let people think about questions and ask questions. By the way, you know, you can direct your questions not only to Barry, but also to Abhijit and Shalini. It's about this lifting of Hilbert-space to Banach space. So I understand that what we are talking here technically is just you take Hilbert-space, and then the lift is just to the bounded operator on that Hilbert-space. But this Banach space can also be a Hilbert space, right? You can, so I just wonder, you know, you can take a Hilbert-Schmidt product and it could be just, why don't you just give it a richer structure? Why
You want to just stay at the minimal level, just define only the norm, don't go any further?
Okay, good question. Yeah, so first I just want to say this lifting idea and being able to connect Banach-space to Hilbert-space is significant. The Choi-Yamakowski isomorphism that's very common is built on this principle, so it's not esoteric. If the Hilbert-space is finite dimensional, then we can say, like, okay, so the Banach space of operators have the norm, but not an inner product. But then in the finite dimensional case, we can lift the inner product structure, loosely speaking, and carry it over. So what you're asking is completely valid, provided that we restrict our results to finite dimensional Hilbert spaces. We want to make sure we keep it, we want to make sure that we don't restrict ourselves away from having results that apply in the infinite dimensional case.
Okay, thanks. So I have one question here. So Varun is asking, are Alice and Bob on equal footing? Question mark. I ask, since the channel mapping operators on one side to those on the other isn't, sorry, I just have some problems. So I ask, since the channel mapping operators on one side to those on the other is lossy, which suggests an asymmetric relationship.
Okay, great. Yeah. Oh, there's more?
Yeah, so there's this question. I have a few more here. By the way, you're most welcome if you want to unmute yourself and fire the question directly. So there's another one. So from Valerio. Valerio is asking, I may have missed this, but if Alice prepares two entangled systems and sends one over to Bob through the wormhole, what happens in this case when they have different inner products?
Okay, so those are two, one from Varun, one from Valerio.
That's right.
Okay.
You know, and yeah, so I'll just wait for more to come, but perhaps you can take those two.
Okay, so first, nice to hear from you, Varun. For people who don't know it, Varun studied in Calgary, so he's it's nice to hear from, it's nice to get a hard question from an alumnus. Varun, can you speak just so I can hear you articulate the question again?
Varun, you can probably unmute yourself and speak.
Yeah, nice to see you again, Barry. Thanks for the nice talk.
I don't see you.
Sorry, I haven't turned on my video and I'm not in presentable condition.
Okay, state the question again.
Yeah, so my question concerns the fact that the channel that connects operators on Alice's side to those on Bob's side, you call it a lossy channel, and that suggests to me that somehow there is a loss of information. So it's like Alice and Bob are somehow not on an equal footing.
Yeah, we have restrictions on it being an invertible channel, but let me just see if Abhijit or Shalini just want to spout out the answer quickly.
Thanks.
Yeah, I mean, I don't see them as being on unequal footing in any sense. In our mind, we do picture that Bob lives in a different PT symmetric universe. But as Barry emphasized through the talk, this PT symmetry is really not observable if one is in his or her own universe. You know, like you need a channel or you need quantum communication to bring out this PT symmetry. So my short answer is that Alice and Bob are really on equal footing, but it's just that the channel, the wormhole that Barry mentioned, is lossy.
I think what he's worried about is that if it loses one way, it'll lose the other way, but that's okay. It could be lossy in both directions.
Okay.
Yeah, it's lossy in both directions. Yeah.
I see.
Exactly. And Varun, just to be clear, like the loss is important because, you know, the superluminality, the break-in the no cloning theorem would work, but, you know, when Alice sends stuff to Bob, there's loss along the way. And if it's the equal footing, you swap them, Bob has to lose stuff sending to Alice. So we do have these channels equally lossy in both directions.
Okay, thank you very much.
Okay,
Valerio,
so then we have a Valerio's question, which basically says, you know, you have Alice and she prepares an entangled state of two systems and sends one through to Bob through the wormhole. So what happens in the case when they have different inner products?
So Valeria, I'm trying to understand exactly what you mean. So I guess what you're asking is, if Alice prepares, say, an entangled pair of photons and sends them through the wormhole to Bob, you're wondering.
No, just one of them goes.
Okay, you're asking. Okay, so if Alice prepares an entangled pair, so like one EBIT, and sends one partner, one of those to Bob, how is that entanglement then described?
All right.
Is that
yes?
Okay. So we have to operationalize it. So if I describe it quantum mechanically, how do I describe it? I might write a Bell inequality, or more generally, I might write a witness. So the description of the entanglement depends on the operational approach to being able to ascertain it. So we would need to write the witness. Now, the classical communication is faithful, but let's say they're testing a Bell inequality violation. So Alice prepares the pair, and if she did a Bell inequality test in her universe, then it would be violated. But she sends a photon to Bob. Bob gets it. His inner product is different. What would then happen would depend on, like, Bob's measurements could be different. For example, if you think of photons, HV and VH, so HV plus VH, a Bell state, the H and the V are orthogonal states in Alice's universe, but they might not be orthogonal in Bob's universe. So the record that they make depends on how that witness is actually affected. So we have to be very careful in defining entanglement in this case.
So does it mean, for example, that in this case, obviously the scalar product of the inner product is different at two places. So that may have seriously affect, for example, the Bell test, if they perform the Bell test, simply because the probabilities, right, for given orientations on Bob's side will be different. So what are the implications of this fact? It could have a serious implications.
Yeah, it does. So just like cloning, so you start to clone, and then what saves standard quantum mechanics is the losses in the channel. So with the entanglement testing, you would expect that losses might occur that cause results that seem counterintuitive but are explained by lossing. We haven't dealt with that case at all. So I expect there to be an effect. I've said that the relative PT symmetry is an observable effect, and what it does to entanglement, I have no idea yet. I don't know if Abhijit or Shalini know what would happen, but I think none of us know what will happen yet.
Okay, thank you.
Thanks. Let's see. So we have one more question. Let's see, I'm trying to... Junie Lee says, perhaps I'm misunderstanding, but did you say that PT violation conservation is not observable locally? Would that also imply that the C violation conservation is not observable locally?
Okay, good question. So there's the subtlety here, which Abhijit mentioned, and I just want to be really clear on. So in particle physics, T is often called parity, but it's a point reflection symmetry. T is time reversal, and then we have the CPT theorem. And the CPT theorem is just charge, what we often call parity time symmetry, and then that's what leads to antimatter being what we know and love. When Bender introduced the PT symmetry, it's a generalized notion. So as Abhijit explained, we have essentially unitary and anti-unitary transformations taking place. So in what we do, there's no connection directly with anything to do with CPT theorem used in particle physics. Now, there could be an implication. So P and T are, there's no reason we can't choose P and T, but we haven't studied the problem yet, so we don't know what would happen to the charge. Like we don't know yet what would be the implications for the CPT theorem.
Right. So one more question is related to the fact that you use detection of entanglement looking at positive but not completely positive maps, which is somewhat related to the relative T-symmetry. Is that in any way modified in your approach? So I guess, trying to sort of reformulate this, if it is not clear, indeed, certain operations like partial transposition that are used for detecting quantum entanglement can be related to inverting time in one location and not in the other. So how does it feature in your approach?
Right, that's related also to Valeria's question on entanglement. And I guess the motivation is like the PPT type questions, positive partial transpose. We haven't studied it yet, so I don't know the answer. Right now, essentially, and I'll tell you why it's not that trivial for us, because so far we're sticking to single particle quantum mechanics. And so these questions about entanglement, positive partial transpose, we kind of need to go to like what I think of as a tensor product structure. Now, Shalini and Abhijit keep correcting me on this because my thinking of tensor product is still a little bit too naive. We have to be very careful with it, but we haven't developed the 2-particle version yet. And that needs to be developed in order to deal with those kinds of questions. So at the moment, at the moment, any questions you ask about 2 particles, we don't know the answer for sure.
Right. So anyone would like to ask questions directly? If just looking at the gallery of happy faces and some names on the screen, but I don't see anyone. Well, thank you, Shalini, thank you, Abhijit, and thank you, Barry. That you left us with, at least me, with lots of things to digest. I think it's certainly something very interesting that you are doing. I'm trying to sort of see through the forest of mathematical formulae that you showed us that the possible physical relevance, and I'm sure there will be something interesting to learn from that. So many thanks, and thank you for joining us. It must be late on your side of the world, even though the inner product might be slightly different. So many thanks, and all of you who missed this talk, and it will be recorded and it will be on our website. And thank you very much. And I do hope at least to see you on the other side of the pandemic curve in Singapore in not too distant future, all of you. So thank you.
Thank you very much, Arthur. Thanks, everybody.